Last class, you learned backtracking on the two most fundamental examples and A202 how, generating all subsets and all permutations. You have the 3-beat rhythm in your fingers now. Choose, explore, unchoose. Today, we take that same technique and point it at the problem it seems almost designed for, the classic constraint puzzle. Specifically, the n queens problem and A212. Place n queens on an n by n chessboard so that no two of them can attack each other. It is a beautiful problem, and it is the perfect vehicle for the single most important idea from last class, pruning. In subsets and permutations, we mostly explored everything. In n queens, exploring everything is hopeless, and 82 on 12. The possibilities are astronomical. What makes the problem tractable is aggressively cutting off doomed paths. The instant a queen is placed where it cannot work. Here, pruning is not a nice optimization. It is the entire game. By the end of this class, you will understand how to structure n queens as a backtracking search, how to check whether a placement is safe, why pruning is what makes it solvable at all, and how this exact same method solves Sudoku and a whole family of real constraint puzzles. Let us solve it. Here is our path for today. First, constraint puzzles as a family. Second, the n queens problem itself. Third, the row-by-row structure. Fourth, the safety check. Fifth, why pruning is the whole game. And sixth, applying the same method beyond the board. Let us dive in. Let us start by naming the family of problems we are entering, because recognizing it is half the skill. A constraint puzzle is one where you must place or assign things such that a set of rules and 812, the constraints and 812 is never broken. Fill in a Sudoku grid so no digit repeats in a row, column, or box. Color a map so no two neighbors share a color. Place queens so none attack each other. In every case, you are building an arrangement piece by piece, and every piece you add must respect the rules given everything placed so far. Backtracking is almost tailor-made for these, and here is exactly why. As you build the arrangement, you can check the rows at every step, and the instant you place something that breaks a rule and 812 or reach a state where no legal placement remains and 812, you know that this entire path is doomed. There is no point continuing to fill in the rest. It can never become valid. So you abandon it and back up, exactly as backtracking does. The rules give you a natural, early signal to stop. This is the crucial difference from last class. In subsets and permutations, almost every path led to a valid answer, so we walk them all. In constraint puzzles, most paths are dead ends that violate the rules early, and the whole art is detecting those dead ends as soon as possible and pruning them away. The constraints are not just what defines a solution, and A2112. They are the tool you use to avoid exploring the vast majority of non-solutions. So the takeaway? A constraint puzzle asks you to place or assign things so a set of rules is never broken, and backtracking suits it perfectly, and 82112, because you can check the rules at each step and abandon an entire path the instant one breaks, using the constraints themselves to prune away the vast majority of dead ends. Let us make it concrete with the classic example, the n queens problem. The statement is simple to say. You have an n by n chessboard and n queens. You must place all n queens on the board so that no two of them attack each other. For a standard board, that would be 8 queens on an 8 by 8 grid, but the problem generalizes to any n. When you have placed all n, with none attacking any other, you have found a solution. To understand the difficulty, recall how queen moves in chess and 8-202 how. It is the most powerful piece. A queen attacks along its entire row, its entire column, and both of its diagonals for any distance. That means a single queen threatens a huge swath of the board. So placing one queen does not just occupy one square, it forbids an entire row, an entire column, and 2 full diagonals to every other queen. Every placement dramatically constrains where the remaining queens can go. And that is what makes it a genuine puzzle rather than a simple task. The constraints interact where you put the first queen shapes what is possible for the second, which shapes the third, and so on. Place a few queens carelessly, and you can easily reach a point where the next row has no safe square at all, an A212, a dead end. The number of ways to place n queens naively is enormous, far too many to check one by one for a large board. We need to be clever, and backtracking with pruning is exactly that cleverness. So the takeaway, n queens asks you to place n queens on an n by n board, so none attack each other. And because a queen attacks along its whole row, column, and both diagonals, every placement forbids large regions to the others and A112. The constraints interact so tightly that a naive check everything approach is hopeless. The first step in solving n queens cleverly is to structure the search well, and one simple insight cuts the problem down enormously. Here is the insight: since a queen attacks along its entire row, no two queens can ever share a row. That means every row must contain exactly one queen n, 812, no more, no fewer. This immediately reshapes the problem. Instead of asking an 8200 where on this whole two-dimensional board do the queens go, at 8200 200, we can go one row at a time, placing exactly one queen in each row before moving to the next. So the choice at each step becomes beautifully narrow. For the current row, the only question is, which column do I place this row and 3 tiny s queen in? There are just n columns to consider, not a whole board of squares. We place a queen in row 1 at some column, then move to row 2 and choose a column for it, then row 3, and so on down the board. When we have successfully placed a queen in every row, we have a complete solution. And this maps perfectly onto backtracking. Each row is a level of the decision tree. The choice at each level is the column, one of n options. We go deeper by moving to the next row, an A212, that is exploring an A212, and when a row offers no valid column, we come back up and change the previous row and tiny 9's choice, an A212, that is backtracking. The abstract recursion tree from earlier classes becomes literally a walk down the rows of the chessboard. Structuring it this way is what makes the whole thing manageable. So the takeaway, because no two queens can share a row, exactly one queen goes in each row, so you solve row by row an A212, and the choice at each row is simply which of the n columns to place its queen in, turning the board into a clean decision tree with one row per level. At the heart of the algorithm is one question, asked over and over: is it safe to place a queen on this square? Let us define exactly what an 8200 200 safe and 8200 200 200 200 means. Because we place row by row, from the top down, any queen that could conflict with the one we are about to place is already on the board, in a row above. So we only need to check against the queens already placed. The first check is the column. Is there a queen in the same column somewhere in the rows above? If so, the square is unsafe and 80A2 foul, they would attack along the column. The second check is the two diagonals. Is there a queen on the diagonal going up and left from this square, or on the diagonal going up and right? A queen anywhere along either of those diagonals would attack our new one. Checking the diagonals is the part beginners find fiddly, but conceptually, it is the same idea. Look back along both diagonal lines toward the placed queens and see if any sits on them. We do not need to check the row, because our row-by-row structure already guarantees one queen per row. If all these checks come back clear, an 80 authol, no queen in the column, none on either diagonal, and 80 authol, then the square is safe and we may place our queen there and regress to the next row. If any check fails, the square is unsafe and we must try a different column. This safety check is the concrete embodiment of the puzzle N39. As constraints, it is the rule checker that lets us prune. Getting it right, an 8212 column and both diagonals against the already placed queens, and 8212 is the technical core of the whole solution. So the takeaway, a square is safe if no already placed queen shares its column or lies on either of its two diagonals, and A212. And since we place top down, one per row, we only check queens above, making the safety check the concrete rule checker that drives every pruning decision. Now we arrive at the beating heart of this class. In n queens, pruning is not an optimization. It is what makes the problem solvable at all. Let us see why. Consider what happens when, in some row, you check all n columns and every single one is unsafe and 8-1-12. Each is attacked by a queen already placed above. This is a dead end. There is no legal move in this row, which means the choices you made in the rows above cannot lead to any valid solution. The correct response is not to guess or push on. It is to backtrack immediately and A204 go back to the previous row. This early abandonment is pruning, and its effect is staggering. The moment you place a queen, it forbids a column and 2 diagonals to everything below, which often makes entire lower regions of the search collapse to dead ends quickly. By detecting those dead ends as soon as they appear, N80 hundo R12, row by row, as you place N80 hundo R12, you skip past enormous numbers of arrangements that could never have worked without ever fully constructing them. You cut off whole branches of the tree near the top, and everything beneath them vanishes from consideration. Contrast this with a naive approach that places all n queens in every possible combination and only checks validity at the very end. That approach examines an astronomical number of full arrangements. Backtracking with early pruning examines a tiny fraction of that because it refuses to build on a foundation it already knows is broken. For a board of any real size, that difference is what separates a solution that finishes in a blink from one that would never finish in your lifetime. Prune early, prune often, and A212. Here, it is everything. So the takeaway, when a row has no safe column, you backtrack it once rather than pushing on an A2121. And because each queen forbids a column and 2 diagonals below it, detecting these dead ends early prunes away astronomically many doomed arrangements, which is precisely what turns in queens from impossible into instant. The real prize of learning in queens is not the chessboard and A2112. It is realizing that the exact same method solves a huge family of important problems. Take Sudoku. You fill empty cells with digits, and the constraints are that no digit repeats in any row, column, or box. Solve it with backtracking. Pick an empty cell, try a digit, check it against the constraints, and if it is legal, link us to the next cell. If you get stuck with no legal digit, backtrack and change an earlier choice. It is choose, check, prune, backtrack, and 80-80 set wolf, identical in spirit to n queens, just with different rules. And it generalizes far beyond puzzles you would find in a newspaper. Coloring a map so no 2 neighboring regions share a color. Scheduling tasks so none conflict. Filling a crossword grid with words that intersect correctly. Assigning resources under a web of restrictions. All of these are constraint satisfaction problems, and all of them yield to the same template. Build the arrangement one choice at a time. Check the constraints at each step. Prune the instant a rule breaks, and backtrack to try alternatives. This is why in Queens is a staple of every algorithms course and AD212. Not because chess puzzles matter, but because it teaches a pattern that appears everywhere in real software, from timetabling systems to configuration solvers. Once you can see a new problem and recognize NA200, this is constraint satisfaction NA212. I place things, I have rules, I can check them as I go. NA221, you already know the shape of the solution. That recognition is the transferable skill this class is really about. So the takeaway, and Queens is a template for constraint satisfaction, and A2112, Sudoku, map coloring, scheduling, crosswords, and resource assignment all yield to the same choose, check, prune, backtrack method and 8200. So the real skill is recognizing a new problem as constraint satisfaction and reaching for backtracking. Let us consolidate the method into a key algorithm and the habits that make it work well. The algorithm is our familiar 3 beats, now guided by the rules. Place, put a queen in a safe column of the current row. Recurse, move to the next row and try to solve it. Backtrack, if the current row has no safe column, undo an A212, remove the previous row and A9's queen, and try its next column instead. Repeat until every row has a queen, which is a solution, or until every option is exhausted. Place, Recurse, backtrack, and A212. The same rhythm as last class, with the safety check deciding each step. 2 habits make this efficient and correct. First, check constraints the instant you place, not at the end and I at 2-1. While this is what gives you early pruning, so build a safety check into every placement. Second, track what is used cleverly, rather than scanning the whole board each time. Keep sets of which columns and which diagonals are already occupied, so the safety check is a fast lookup rather than a slow search. That small optimization makes a real difference on larger boards. And the third habit, the one people get wrong, undo cleanly when you backtrack. Every time you remove a queen to try elsewhere, you must fully restore the state and 82 hundo have, free up that column and those diagonals and 82 hundo have exactly as it was before you placed it. A forgotten unmark leaves phantom constraints that corrupt the rest of the search. Choose, check, prune, and undo faithfully and A212. Do those 4 cleanly and backtracking will solve constraint puzzles reliably every time. So the takeaway, the algorithm is place a safe queen, recurse to the next row, and backtrack when stuck, and A212 made efficient by checking constraints the instant you place, tracking used columns and diagonals for a fast check, and undoing cleanly on every backtrack so no phantom constraints linger. Before we recap, let us step back and appreciate what you have actually gained, because it is bigger than one puzzle. You now have a complete, reusable method for an entire class of hard problems. Many problems that look intimidating and A212, scheduling, assignment, configuration, puzzle solving, and A2121 are, underneath, constraint, satisfaction problems. Before this class, they might have seemed to need some special, clever, one-off trick. Now you can see them for what they are and reach for a method you already understand, model the choices, define the constraints, and let backtracking with pruning search the space intelligently. Just as importantly, you have internalized the single most valuable instinct in this kind of search: fail fast. The whole reason backtracking is practical is that it refuses to waste effort on paths it can already tell are hopeless. That instinct, an 84-1, check as early as possible. Abandon a doomed path the moment you recognize it. An 84-1 is not just an algorithm technique. It is a way of thinking about problems that pays off far beyond code. Turn and EC9, pour effort into a plan you already know is broken. And you have seen, concretely, that the difference between a naive brute force search and a well-pruned one is not a small speed up, but the difference between impossible and instant. That lesson, and 8080 ball, that how you search matters as much as what you search, and 8080 file sits at the core of computer science. Carry the N Queen's pattern with you, and a whole category of problems that once looked unsolvable will look, instead, like a decision tree waiting to be pruned. So the takeaway, you now hold a reusable method for constraint satisfaction and the fail-fast instinct behind it, and A212 well. Abandon doomed paths early in A212. And you have seen that good pruning is the difference between impossible and instant, which is why how you search matters as much as what you search. Let us gather the whole class in one breath. Constraint puzzles ask you to place things, so rows are never broken in A212, ideal ground for backtracking. N queens is the classic, place N queens, so no two share a row, column, or diagonal. Because no two share a row, you place one queen per row, choosing its column. The safety check asks, is any placed queen in this column or on either diagonal? If no column is safe, you backtrack it once and A212, and that early pruning is what makes it solvable. And the very same choose, check, prune, backtrack template solves Sudoku, scheduling, and coloring. Next class, NA-A212, Dynamic Programming, remembering results to avoid repeated work. One idea at a time. That is backtracking 2